Good day. If you are watching this, I suspect you are serious about seeking means to a cleaner energy future. A key to that future involves creating practical means for energy storage. This is the core mission for ezNGsolutions. It is well known that the push towards intermittent power actually increases the need for natural gas. And we know that LNG will play a huge role for consumers generally wanting a greener fuel supply. However, there is real pressure to find a cleaner alternative because many people realize that LNG has a large carbon footprint. Still, it is expected that LNG demand will double by 2040, and we often see that expanding natural gas markets have a need for local storage. Many parts of North America must depend on surface storage, usually in pipelines or as LNG. Texas's big chill in 2021 has highlighted the value of having storage adjacent to power generation. In addition to onshore and at-shore storage for power generation, ezNG will support the shipping industry's drive to adopt cleaner fuels, starting with LNG. So let's look at ezNG's cold liquid storage technology, where pressurization forces are balanced by adjacent cells. Low-cost, mass-produced cells can efficiently fill available storage spaces. Cell arrays and reinforced structures safely store LNG at low temperature and low to moderate pressures. On land, cells are secured in concrete vaults. For the maritime industry, much larger cells can fill insulated cargo holds in ships or barges. To store fuel on ships, GTT has proposed its low-pressure LNG brick tank concept. This independent prismatic tank involves complex manufacturing. The German tank manufacturer TGE has recently provided marine fuel storage using big pressure-competent cylinders. An ezNG fuel tank can be designed to hold just as much LNG at the same or higher pressure rating while occupying less hull space. Only 5 flasks are needed if the cells are designed to be as tall as TGE's big cylinders. More space is required if you want to segregate 6 cells into 2 tanks. Now we'll show 3 uses for ezNG's two-sided flask cells. From easily transported mass-produced cells for onshore fixed storage projects to important ocean and rail transport options. Ships fitted with ezNG cells have an edge in overall sizing for transport of LNG to stranded markets. Railcars can be designed for cargo or fuel transport. This slide introduces ezNG's alternative to the LNG fuel bunkering barge being built for Polaris. ezNG cells are much less costly than big vacuum-insulated bullet tanks and can be fabricated on-site instead of being imported from China. Further, ezNG cells for LNG cargo storage require much less internal hull space, so the barge can be smaller, or wing tanks can be designed along the length of the hull to reduce the risk of cargo release in the case of a collision. Now, most power developers will want storage permanently secured nearby the power plant. ezNG has been working with a major U.S. pipeline owner to address supply pinch points on their system. While we are constrained from revealing all details, key features of this simple concept are obvious. This barge can receive LNG from a matched liquefaction facility onshore or delivered by a bunkering barge. While we know ezNG can cost-effectively serve the needs of a growing LNG market, we are excited that our technology opens the way for cleaner options. Many companies are already looking for carbon-free fuels, and because it is a very dense hydrogen carrier, green ammonia is likely to be a real game changer longer term. The EDF has already proposed that ammonia is the best option for maritime fuels long term. Near term, there's pressurized LNG. PLNG was invented over 50 years ago as a sweet spot for liquefying natural gas for global transport. This graph shows how PLNG avoids the costly containment needed for CNG on the right, as well as the high energy needed to produce conventional LNG on the left. In fact, ExxonMobil reported that LNG requires twice as much energy as PLNG. Unfortunately, there were two big problems way back then. First, there was no practical concept for storing large enough quantities for ocean transport. And second, prices for natural gas fell so much that the LNG industry collapsed for years. Pressure-competent storage technology allows the adoption of both ammonia and PLNG as fuels for the energy transition. But one might ask, the LNG industry has been going strong for many years now. If PLNG is so great, why hasn't it already displaced LNG? 25 years ago, ExxonMobil thought PLNG was attractive enough to invest tens of millions into R&D. Here's a summary of the key advantages Bowen reported in 2005. Pretty impressive, eh? So why did ExxonMobil drop the ball? One can guess that PLNG was competing against its own mega-scale LNG projects. So the ship for this very special remote project was designed with 200,000 cubic meter capacity. This was much more than typical for LNG carriers of the day. PLNG projects also require pressure-competent containment throughout the supply chain, and the big cargo storage cylinders were a problem. The patented high-strength, low-temp steel and welding required intense R&D efforts and would be very costly compared to commonly available cryosteels. Also, tanks made of this material were unable to even carry common LNG. It was challenging and expensive to secure these big cylinders into the ship's double bottom. So, around 2005, the PLNG initiative was shelved. What we have discovered is that ExxonMobil and the world needed a simple and efficient pressure-competent storage technology. Now, I should point out that PLNG is only about 80% as dense as LNG, so to carry the same amount of regas fuel, the tanks must have 25% more internal volume. Still, this slide indicates how the right tank technology allows a switch to the much greener PLNG while getting more than twice as much energy into a vessel just slightly larger than the Polaris barge. It's also worth noting that ezNG's tanks can carry either LNG or PLNG. Let's take a moment to consider an option many carbon-free world proponents are pushing. Battery storage facilities are being deployed today, with an expensive 100 megawatt system already set up in California. It is probably no surprise to this power form that LNG storage is much cheaper than the battery option. However, it's important to note that PLNG is even less costly and will produce 100,000 tons less CO2 than the LNG option over a 20-year life. As highlighted by the previous slide, most popular decarbonization initiatives result in much higher costs for energy. CCS is very complex and costly, so it's important that we find and adopt ways to constantly and substantially reduce our CO2 output. We know that natural gas is a great alternative to coal and black oil-based power gen. We also know that intermittent energy sources need storage media to have any viability. Therefore, the world will continue to seek liquefied natural gas as the fuel for low-cost, cleaner power throughout the energy transition. However, now that a suitable containment technology exists, the industry should focus on PLNG as the way to reduce both costs and CO2 output. Our low-carbon future depends on practical means for energy storage. Because PLNG is simpler and costs less than LNG, it provides a great opportunity, not a burden, for reaching your carbon reduction goals. Thank you all.